Okay, so of course you were very young. Well, you probably know you would have. You'd have to be 40 years old. But how many have like heard of the space shuttle and the space shuttle program? They're not using it. It's not being used. My understanding anymore at NASA. But how many have heard of the space shuttle? Okay, excellent, excellent. Many of you have, absolutely, absolutely. And you know, we're going to learn about something called vector spaces. And every time we go into a new chapter, there's always an introductory example. And you know, you can read through this, but they mention that mathematically, input and output signals to an engineering system are functions. Okay. And it's important that the functions can be added and multiplied by scalars. One moment, hold on. Well, yes. I'm trying to recall here, Shivani. There were two shuttles where the I think it was maybe it was Challenger, where the people I believe it was Challenger, where the people died. And then there was another one also. I forget, Discovery. I forget, but yeah, Challenger I believe was the first one. And it had to do with the seals, the O-rings. But the mathematical, good question. There were multiple shuttles produced, but the mathematical foundation system for engineering, for systems of engineering, and the shuttle was a system for engineering because you needed input and output signals to the engineering system. The mathematical foundation for systems engineering rests on vector spaces of functions. Okay, vector spaces of functions. And vector spaces arise in engineering, physics, and statistics. Okay, so we need to focus first on, hey, you know, what is a vector space? What does a vector space mean? So let me get right to the definition of a vector space, which is section 4.1, vector spaces and subspaces. Okay, so a vector space has to satisfy these 10 axioms. These 10 axioms. And the axioms are axioms that you have actually seen before. You just didn't, like for instance, when you add vectors in two-dimensional or three-dimensional space, if you consider the normal mathematics of vectors in two-dimensional and three-dimensional space, you're working in a vector space because all of the rules, all of the axioms given here, axioms 1 through 10, those are vectors, like vector addition, vector multiplication. No, not multiplication, but multiplying a vector by a scalar, adding vectors, subtracting vectors. All of these properties are ones that you are aware of when you work with a two-dimensional or three-dimensional vector space. Just without even knowing linear algebra, right? So you've been working in vector spaces in your math career. You just didn't know it. But we can be a little more formal in our ideas of vector spaces. So, like for instance, let me go here to a few examples here. I want to get right to, I want to go to example 4. Okay, example 4. So if you have the set, the space P sub n of polynomials of degree most n, that space is going to, a vector, okay, if your space is the space of nth degree polynomials, the vector then here, what is the vector? Well, in this case, it would be this nth degree polynomial, where the coefficients, okay, well, a sub 0 is just a constant, but the rest are coefficients. But a sub 0 to a sub n and the variable t are real numbers. Okay, it turns out that this space of vectors, where the vectors are polynomials, is actually a vector space. It meets the 10 conditions given that you just saw for a vector space. So like one of the conditions of the vector space, for instance, one of the conditions, let me just hold on here. Well, well, I want to be a little careful. Like for instance, the zero vector. The zero vector, okay, has to be, if you have a set of vectors, and for those set of vectors to form a vector space, the zero vector has to be in the space. Well, okay, if you have this polynomial space, is 0 in the space? Well, it is, because if all coefficients are 0, okay, then P, if all coefficients are 0, then you have the 0 polynomial. Okay, that's the 0 polynomial. In other words, let me be a little more clear here. Okay, so if you have, like, let's say you're talking, let me just make sure I'm doing this right. Yeah, let's say you're talking the vector space P sub 2, which is the space of all second degree polynomials. Well, all second degree polynomials, if those are the vectors you're talking about, all second degree polynomials would have to be able to be written in this form. Okay, have to be able to be written in that form. Well, one of the axioms is that if you look at the definition of a vector space in the beginning of section 4.1, one of the axioms is that the zero vector, okay, is that there is a vector 0 vector, such that u plus 0 equals u. So in other words, if you have, I want to say this the right way, class. I want to say it the right way. If you were to take 0 plus 0 times t plus 0 times t squared, okay, all right, and add that to A sub 0 plus A sub 1t. I want to be a little bit careful here. Plus A sub 2t squared. Okay. All right, what would, and we'll call this vector u, because that vector u is in the polynomial space. Okay, it's a member. Think of it like a member of a club. That vector u is in the polynomial space. Okay. Now, if you add this vector here to the vector u, do you get back the vector u? Is this a true statement, what I wrote here? It is. And so this here, we call that the zero vector. But the point is, the zero vector is the zero vector in this polynomial space, P sub 2? It is, because this zero vector can be written as sum A naught, that's, in that case it's 0, plus A1 times t, A1 is 0, and A2 times t squared. A2 is 0. The point is, there is a zero vector in this polynomial space here, such that 0 plus u equals the vector u. And that confirms axiom 4 from the definition of a vector space. Okay, so we just confirmed one of the axioms, and the other 9 axioms will follow as well. So the operations that you do with polynomials, you know, where you add them, subtract them, multiply them through by a scalar, okay, the polynomials satisfy the axioms for a vector space, because you can add polynomials, you can subtract polynomials, you can multiply polynomials through by a constant, and the resulting polynomials are back in the vector space. So that's like formally how you use the definition of a vector space to show that a set of vectors is a vector space. But the problem, I mean, that's fine, But oftentimes we don't need to be, we can get away a little easier. We can find an easier way to show that we have a vector space. Okay, and that's where subspaces come in. So subspace, okay, a subspace, well, hold on, let me just sort of go right from the reading here. In many problems, a vector space consists of an appropriate subset of vectors from some larger vector space. In this case, only 3 of 10 vector space axioms needs to be checked. The rest are automatically satisfied. And in fact, a vector space is itself a subspace. So a subspace of a vector space is a subspace H of V that has 3 properties. Okay, first one is that the zero vector of the vector space is in the subspace H. Okay, and we'll do an example to show this. The second property is that H is closed under vector addition. That is, for every vector u and v in H, okay, for every 2 vectors in H, the sum of the vectors is back in H. That's called closure under vector addition. And finally, your subspace H here has to be closed under multiplication by scalars. So for every vector u and h and every scalar c, the vector c times u is back in the subspace H. Okay, these are your three properties for a subspace to show that you have a subspace. And we're very interested in subspaces. We're very interested. Okay, so if we look at a few examples of this, let's look at a few examples. Let's go to example 7 here. Example 7 says, let P be the set of all polynomials with real coefficients. Then P is a subspace. Why would that be? Why would that be? Well, okay. First of all, the zero polynomial is in the subspace. Okay, it's in this subspace P because the zero polynomial can be written as a polynomial. Zero can be written as a polynomial. It's just all the polynomial, all the coefficients are zero. Secondly, the sum of two polynomials is also going to be in the space. If for instance, if you add two third-degree polynomials to each other, what do you get? If you add a third-degree polynomial with another third-degree polynomial, what's the degree of your resulting polynomial going to be? It's going to be good, Haley, good to funny. It's going to be a third-degree polynomial. Okay. Finally, if you were to take a scalar and multiply it through by a polynomial, does that change the degree of your polynomial? No, it doesn't change it. So that is back in that's in the subspace. So that proves that the set of polynomials with the real coefficients, that polynomial space is a subspace. Okay. Now, there is an important result here, and I want to try to give you a little time to work in class here. But okay, if you have a subspace, well, if you have a span of a collection of vectors, okay, that span of the collection of vectors is actually a subspace. Okay, so you remember spans of vectors, right? You had that on your first exam, span of a set of vectors. The span of a set of vectors is actually a subspace. And they prove it here in example 10. Okay, they prove it in example 10. They say, all right, given that you have vectors v1 and v2 in a vector space, let H be the span of that vector space. Let H be the span of vectors v1 and v2. Show that the space H is a subspace of V. Okay, well, to show that, we need to verify that the three properties of a subspace, okay, outlined here, hold. So first of all, we need to show that the zero vector is in the space H. Okay, so if we go back here, all right, consider the zero vector. The zero vector can be written as 0 times v1 plus 0 times v2. So because of that, that means that zero vector is in the span of v1 and v2. Okay, so the zero vector is contained. The zero vector is in our space H. The zero vector is contained in our space H. So that's the first condition of a subspace is satisfied. The second condition of a subspace is to show that H is closed under vector addition. Right? That's the next thing we have to show. Well, what we can do is we can take two vectors, vectors u and w, which are each written as, the vector u is a linear combination of vectors v1 and v2. So the vector u is in the span of v1 and v2. And the vector w is also a linear combination of vectors v1 and v2. So w is in the span of vectors v1 and v2. Okay, well, let's add vectors u and w. Let's add them together. If we add u and w together, all right, we can group together. Well, we can rewrite the sum of the two vectors, okay, like this, as this. And, well, that's just a linear combination of vectors v1 and v2. So u plus w is going to be in the span of v1 and v2. Is that clear on that why H is closed under vector addition? All right, thank you, Nafani. Are there any questions so far? All right, thank you, Naima. Makes sense. Good, good. Well, the third step, part C, is we want to show that H is closed under multiplication by scalars. So I'm going to take my vector u, and multiply it by a scalar c. Okay, well, then c times the vector can be written as this, cs1 times v1 plus cs2 times v2, which shows that c times u is in H, and so H is closed under scalar multiplication. Thus, H is a subspace of V. So anytime, whoops, hold on. Anytime you have a span, I mean, we did this for this, we showed that the span of two vectors, v1 and v2, is a subspace. But in fact, it can be generalized. But in terms of like a picture of this subspace, what does this subspace look like? Well, here it is in figure 9. This is the span of v1 and v2. Okay, and the subspace is simply a plane. The subspace, it's a little bit much to highlight here, but maybe I'll have to highlight it. The subspace is simply a plane through the origin. So we know what the span of two vectors v1 and v2 is. We know it's a plane, and we know it passes through the origin. Well, now you have a picture of a subspace. A plane, incidentally, as they show in figure 9, would be a subspace of what larger space? A plane is a subspace of what larger space? A plane is a subspace of what space? Well, looking in figure 9, where does that plane live? Good, good, Nafani, good, Catherine. It lives in R3. R3. Subspaces are, they can be subspaces can be, are themselves a vector space, but the span of vectors v1 and v2, which is a plane in R3. It's a subspace of the vector space R3. So basic, and this can be generalized. They want to be a little careful how I say it, but if you have, by theorem 1, if you have any set of vectors in a vector space V, then the span of those vectors is automatically a subspace of V. And we call the span of the vectors the subspace. The span of those vectors is the subspace generated by the vectors. You're generating a subspace. Okay. And the set of vectors is known as your spanning or generating set. It's a term you're going to hear a lot. You're going to hear a lot. Okay. So let's look at an example here. Let's look at an example here. Let me go. Are there any questions so far? I want to bring one. I want to get one example for the notes. But are we, so far we're good? All right. Let me bring up my note here, notes. Okay, let me give you a moment to copy this example down. Okay. Okay, so we want to determine if the following given set is a subspace. What this set here, where does this set live? I mean, this set is a subset of what space? This space W is a subset of what space? Okay, R4. And I appreciate all responses. So how many entries comprise each vector in the space? How many entries? Here's a vector. Vectors in the space have to meet this form here, where S and T are real. So for every vector has how many components? 4 entries. That means 4 components. So these vectors, these vectors live in R4. So my space W lives in R4. And in fact, would it be okay to, I mean, this statement's correct, where I write this like subset here, but could I remove this little piece here? Would this be okay to say? Or do I need to write this? Let me ask you this. Okay, hold on. Let's just do an example here. I just want to ask you this. Is this true? This first statement is R sub 4. So now I'm going to get back to the example here, but I'm just asking, is R sub 4 a subset of itself? Is this statement right, what I wrote here? Can a space be a subspace of itself? Yes, absolutely. Absolutely. But so what's the difference then between what I wrote here and what I'm writing here? Proper subset. So so this I can't say. Okay, so what I'm trying to say is I want to say this the right way. Hold on. I actually want to say this. This is got to be a little bit careful. Would it be okay to say that this space W is a proper subset of R4? Yes. Is it okay to say that, to add this? It is okay, because all that means is space W is either a proper subset of R4 or equal to R4. And it's not equal, but it is a proper subset. Okay, so, but clearly we know that space W is not equal to R4, right? I mean, it's a little better to say this, right? Because we know this space W is not equal to R4. Because there are restrictions. There are these restrictions on space W. So let me ask you, R4 is a 4-dimensional space. If space W here is a subspace, what would the dimension be, you think, of that space, of space W? And this is going a little bit ahead we're going to learn this a little bit more, but I'm just trying to give you an intuitive feel. R4 is four-dimensional space. The dimension of R4 is four-dimensional. What do you think the dimension of W is? If you had to say, okay, the dimension DIM of W. Yeah, it's going to actually be two-dimensional space. Two-dimensional space. So let me show you why. And Benjamin, you're right, and Catherine, I'll show you why. Let me go to the next page here. So I let U be a vector in space W. I can take the vector U, which can be represented, which has to be able to be written in this form with those four components, S minus 2t, 3s plus 5t, 2s plus t, and 4s. And okay, thank you, Catherine. And I can rewrite that as a linear combination of two linearly independent vectors, v1 and v2. Well, W is in the span, W then, space W, can be represented as the span of v1 and v2. That shows that space W is a subspace of R4. And in fact, because v1 and v2 are linearly independent vectors, and there are two of them, that means that the dimension of my space W is two. In other words, space W is a two-dimensional subspace of R4. Catherine saw that right away. Excellent, excellent. Okay, and so all we had to do was show that a vector U in space W is a linear combination of these two linearly independent vectors, v1 and v2, and so W is a subspace of R4. Okay, are there any questions on what I just did here? Are there any questions at all? All right, let me stop the recording.